Welcome back to real analysis. Now that we have already proved square root of 2 is not rational number, we're going to take this to one step further, and we're going to prove that square root of prime number is not rational, where p is prime. Let's go on and prove this. Let us assume the square root of p is rational number, and we can write this as, in terms of fractions, a over b, where a and b are natural numbers. Let's assume that we can do this. Then let's see if this leads to some false results or contradiction or not. If that's the case, then p should be a square over b square. Then a square should be p times b square. Okay, since a and b are natural numbers, let's decompose a and b in terms of their prime factors. Let's say we need all the prime numbers from 2 to the q. Let's say a equals 2 to the power m1, 3 to the m2, all the way to 5, 7, 9, all the way up to q to the mn. You may not be feeling comfortable with this. Let's see what it means. Suppose a equals 28. Just for the sake of it, 28 can be written as 2 times 2 times 4, right? That's 2 square times, 2 times 2 times 7. What am I doing? Times 7, right? 2 times 2 is 4, 4 times 7 is 28. That can be written as 2 to the 2 times 7, isn't it? So if a is 28, then 2 to the power of 2, 3 to the power of 0, and the largest prime number we need would be 7, and 7 to the power of 1. So this would be 2, this would be 0, all other would be 0, and this mn would be 1, and this q would be 7. So any prime number, any number, natural number, let that be prime or composite, we can decompose that into prime. If it's prime number, then all the numbers before it would have power of 0, and only that number would exist, but that will still exist, isn't it? And same way we can decompose b in terms of the prime factors: 2 to the power n1, 3 to the n2, all the way up to, let's say, the largest prime number we need. It doesn't have to be the same because they are different number. Let it be r could equal q, couldn't equal q, but it doesn't matter, to the power of nk. Let's say we have decomposed a and b in terms of their prime factors, and let's see how this leads to contradiction. Let's plug back these prime factors back into the equation. So that should give us a square. It means a times a, so everything would appear twice. So 2 to the power twice m1, 3 to the twice m2, all the way up to q to the twice mn. That's the left hand side. The right hand side should be p times 2 to the twice n1, 3 to the twice n2, all the way up to r to the power of twice nk. So our equation turns this. Let's see if this can be true or not. P is a prime number, so if p isn't any of the numbers from 2 to the q, then there's no way that this could, since p has appeared on the right hand side and p hasn't appeared in the left hand side, and all the numbers here are prime numbers, then that would already be false. So let us assume p is one of the numbers here from 2 to the q, one of the prime numbers appearing in the left hand side. Let's see all the numbers here, since we have squared a, so all the prime numbers here has appeared even number of times. 2, 3, 5, 7, 11, all has appeared even number of times. In the left hand side, all other numbers have appeared even number of times except for p. P has appeared only once, or if p is one of these numbers, then it has appeared even number of times in this part, and one extra p. That makes p appear odd number of times in the right hand side and even number of times in the left hand side. What this means is the whatever we have assumed can't be true, because we have assumed some prime numbers, some product of prime numbers in the left hand side and product of some other prime numbers in the right hand side, and p has appeared false number of times, which can't be true, right? For example, 2 times 3 times 3 times 7 can't be equal to 2 times 3 times 3 times 3, right? Because 3 has appeared 3 times here, 3 has appeared twice here, it has appeared odd number of times in the right hand side and even number of times in the left hand side, so this can't be true. In the same way, this equation can't be true either. That's why our assumption was wrong, and square root of p can't be written as a over b, where a and b are integers. In other words, root p is irrational. It isn't rational. Hope you enjoyed this video. Thanks for watching. Please like, comment and subscribe. Peace out for now.